Hi, this is Scott Vaughn, and this is part one of a three-part series I'm starting on calculus, physics, and rocket science with Kerbal Space Program. In this first part, we'll travel to the moon, well, Kerbin's moon, which is called the Mun, and on the way, use calculus to compute the slope of the tangent to the transfer orbit. We'll also compute the flight path angle, or pitch, of the spacecraft as it travels to the moon. In part 2, we'll land on the moon and do some of the mathematics of navigation to explore around the moon, and in part 3, we'll return to Kerbin, studying the mathematics of orbits, energy, and angular momentum. Today, I'm flying this rocket called the Unity Mark IV, which I found on the Kerbal X website. I picked this rocket because of the recent announcement that SpaceX Starship could potentially serve as a moon lander for NASA. And the Mark IV was easy for me to fly, and it didn't explode too often, even with me at the controls. So thank you to user Janice92 for posting this on Kerbal X. This is a real Kerbal version of the SpaceX Starship, and as I was making this video, Janice92 uploaded a newer version, the Mark V, which has enough fuel to reach the planet Duna, but the Mark IV works perfect for my mission today. I won't focus on all the details of the launch here. In this video, I'm using the mod called Geogebra as an autopilot to launch the Mark IV into a circular orbit about Kerbin, reaching an altitude of 100 kilometers. This means we'll have an orbital radius of 700 kilometers from the center of the planet Kerbin, and due to Kerbin's mass, we need to reach an orbital speed of about 2,246 meters per second. The material that we'll cover here in part 1 of this series is finding derivatives with polar functions, which is traditionally a topic in undergraduate calculus 1 or 2, but we'll also do a lot of physics, and of course what we're doing is real rocket science, at least a real introduction. And this is my goal. I could be doing the calculus on a whiteboard and drawing pictures by hand to illustrate the concepts, but what I have here with KSP is a fun way to illustrate the concepts in a way that is interactive and dynamic. Kerbal Space Program is really a perfect textbook model of Newtonian physics, and thus it follows precisely what is presented in a traditional calculus class, but it adds a fun way to engage with and learn these concepts. Okay, let's pause there. We've got the rocket in a nice circular, stable orbit around Kerbin at an altitude of 100 kilometers. We'll pause and go back to this website I have, sites.google.com, view KSP math, and we're going to try to reach the Mun. So let me scroll down here to this pre-calc chapter, and what I want to do is, there's a picture here, right here. So we're currently in this orbit 1. Circular orbit around Kerbin. This C, point C, is the center of the planet Kerbin, and we're in an orbit with a radius R1. And in order to reach the moon out here in orbit 2, we need to follow a transfer orbit, which is called the Hohmann transfer orbit. So we have to increase our speed to follow that elliptical orbit out there. And so the way we do that is to use this formula for the delta V that's required. That is the change in velocity. So this is something I've already done in a separate video. I don't want to spend a whole lot of time on it here, but I just thought it would be worth briefly mentioning that this calculation, you can learn more about it here. Mu is the gravitational parameter of whatever the primary mass is. In this case, it's Kerbin, so that's a constant. R1 is the current circular orbit radius, and R2 will be that radius of the Mun that we're trying to reach. So you can learn more about this formula there on the workbook, and of course Google search it, but I also have a calculator here on this site. Calculate delta V for the Hohmann transfer. So opening up this, I already have set the radius 1 for the circular orbit, it's 700,000 meters because it's an altitude of 100,000 meters and a radius of the planet of 600,000. And I want to reach the Mun, which has a orbital radius of 12,000 kilometers, or 12 million meters. And so that's the radius of the Mun. This is the gravitational parameter of Kerbin, and this calculation comes from exactly this formula right here for the initial burn to initiate that translunar injection. That's the initial burn that starts us on the transfer orbit. So we need about 841 meters per second added on top of the initial speed that we have in the circular orbit. So that means you're thinking 2246 plus 841, and that's roughly 3087. Actually, we can also visualize that here. Let's go back to velocity with elliptical and hyperbolic trajectories. Click on this one. So if our speed is 2246, we're going to be in this circular orbit. That's the speed required to maintain a circular orbit at 100 kilometers above Kerbin. But if we increase that speed up to about 3087, where you can see that my trajectory is becoming more and more elliptical, the eccentricity is increasing toward 1. Actually, if you blow past 1, it becomes a hyperbolic orbit, which is going to escape the gravity of Kerbin. So that's too fast. 3,500 meters per second is too fast. Let's bring that back down to something around around 3087, and that will reach right out to about where the Mun is. So this is roughly the target eccentricity, the target speed for the translunar injection. Let's see what actually happens back in the game. So here we can see that the orbit is currently circular, and the speed right now is at 2246.4 meters per second. Out here is the Mun. The Mun's altitude above the surface is 11,400,000 meters, but from the distance from the center of Kerbin to the Mun is 12 million meters. We can see on the screen right now that the apoapsis at 100 kilometers and periapsis at about 99 kilometers. It's very close to a circular orbit. Eccentricity is pretty close to 0. The speed jumped up to 2248 meters per second because I think we're approaching a little closer to the periapsis at this moment, so the speed's a little bit higher. And the periapsis is a little bit lower than 100 kilometers, and so the speeds increase just a bit. So we're going to find some point on here to add a maneuver, increase our speed by 841 meters per second, and that gives us the transfer orbit out to the Mun. So now I'll adjust that to where we initiate that injection burn so that we reach the Mun altitude when the Mun is there, right? So at the apoapsis, or as we near the apoapsis, we'll enter the Mun sphere of influence. So this is adjusting the point at which that maneuver occurs. So there I can see that the intercept with the Mun sphere of influence occurs. And this is something I learned from Mike Aben. If I put a focus view on the Mun, I can see what the trajectory would be as we approach the Mun, and I'm going to now add another additional maneuver in here. Or actually, this is just going to, what I'll do is I'll just adjust the timing of that burn so we can try to reduce the periapsis so we get really, really close to the Mun. So I had it there about 100,000 meters, but yeah, settle with about 350. That looks close enough. We'll adjust again as we approach the Mun. This would be the trajectory. So this is here I'm adding that maneuver, that extra maneuver to reduce the speed as we pass by the Mun so that we get captured by the Mun's gravity and enter into an orbit around the Mun. So this is still kind of elliptical. We adjust a little bit the timing of that. We could get closer to a circular orbit. So that'll be a second burn near the Mun when we get there. So now we just wait till we reach that maneuver and fire the rocket's prograde to increase the speed up to the speed required for that transfer orbit. So I can see that maneuver node's approaching in about a minute, and it's going to be a 32-second burn that's required. Current speed about 2245 meters per second. Okay, so now we can see the orbit starting to increase in size and become more and more elliptical. The apoapsis, the furthest point, is getting further and further away from the planet, and the orbit is becoming more elliptical and approaching the desired transfer orbit. The engines are continuing to burn to increase the speed up to about 3080 meters per second, and now we are on this transfer orbit. Alright, so yeah, we hit about 3080 meters per second there, and now we're on a trajectory to reach the Mun. And that 300 meters per second that's on the screen right now, that is the second burn that I'll do to get captured by the Mun's gravity and enter into an orbit about the Mun. So I'll note that we are currently at about 31 minutes mission elapsed time as we start this trajectory toward the Mun. The rocket had kind of flipped around to be oriented for the required burn at the Mun, so I'm going to flip it back to point in the direction we're traveling, in the prograde direction. And that's it. We are on our way to the Mun. Okay, so back here on my website, the Kerbal Math and Physics Lab, down in the Chapter 4, Calculus with Parametric and Polar Equations, there's a section here, Tangent to Flight Path and Pitch, where I go through all of this math that I'm about to present. And that's where you will find this text here. So what it says is an elliptical orbit can be written in the polar form r equals a times 1 minus e squared over 1 plus e cos theta. A is the semi-major axis of the ellipse, e is the eccentricity, theta is the true anomaly, and r is the radial distance from the primary to the orbiting body. So r is this distance here from the primary body. This is where Kerbin would be. This is the center of Kerbin. And this is the rocket. But this would apply for any planet orbiting a sun, or any moon orbiting a planet, or any satellite orbiting any other body. So the periapsis is the point in the orbit where we're closest to the primary body that's being orbited. That's the apoapsis. That's the point that we are furthest from the primary body. And this angle here, theta, this angle theta is the true anomaly, which is the angle measured from this line out to the periapsis to the point on the path where the orbiting body currently is. So this orbiting body is this little m. So as we look down here below, it says, assume the orbital plane is the xy plane. So this is orbiting in the xy plane, and if we do that, what's happening is this will be the x-axis, this will be the y-axis. That happens when you use this form, the polar form. You actually get the origin of the xy plane to coincide with the primary body, and this angle theta. The true anomaly is that angle in standard position in the xy plane. Number 1 says, use the polar form of an elliptical orbit given above to find a formula for dy dx, the slope of the tangent to the flight path in the xy plane. So what we're doing is we are finding the slope of this tangent line. And that slope would indicate the direction that we're traveling along the elliptical path. So given an equation in polar form that corresponds to some curve in the xy plane, we can find dy dx as follows. What we'll do is we'll have to convert the polar form into rectangular coordinates. So those are our conversion formulas from polar to rectangular, but in this example, r is not a constant here. Of course, it's given by this polar function. So let's substitute that. So that's substituting r into each of these conversion formulas. And for the purpose of doing a derivative, we'll rewrite it like this. When we take a derivative with respect to theta, this a times 1 minus e squared is all constant. They are constants for the ellipse. They are fixed values for a particular ellipse, and they will not change with the angle theta. So let's rewrite it like this, where we just sort of factor out this constant to the side. So now that we have our x and y in terms of theta, we can take a derivative and we can calculate what is dy dx. So the way that we find dy dx is we'll find the derivative dy d theta, and then we'll divide by the derivative dx d theta. That's just kind of neat to think about. If you know the rate at which y changes with respect to theta, and similarly the rate at which x changes with respect to theta, dividing them will give you the rate at which y changes with respect to x. So we're going to do each of these derivatives with respect to theta. Let's start with the first one, dy d theta, which is here. So if we have y is a times 1 minus e squared times this fraction sine theta over 1 plus e cos theta, we can do the quotient rule here to get a derivative. dy d theta would be the constant a times 1 minus e squared, and then quotient rule, what I'll do is I'll take the denominator, square it, copy that denominator on top, and then do the derivative of the top, which would be cos theta. And then by quotient rule, you have to do a minus the top, the numerator, times the derivative of the bottom, and the derivative of this denominator here, derivative 1, that's 0, derivative of e cos theta, e is a constant, so we get e times negative sine, or let's just say negative e sine theta. And let's try to simplify this. I'm going to distribute here, and when you multiply here, you get positive, because there's two negatives, e sine squared theta, everything divided by 1 plus e cos theta squared. At this point, we could factor out an e, and we have cosine squared plus sine squared, which is 1. So we get cosine theta plus e times 1. So that's dy d theta. Let's do dx d theta the same way, but I think what I'll do here is speed up. So if you're a student in Calc 2, this would be a good thing now to try. See if you can get the same thing. We're going to do dx d theta. We're going to use this expression here for x, and we'll take a derivative with respect to theta, and then see if you get the same thing. Okay, so there's my result for dx d theta, and now that we have that, we'll go back and actually find dy dx. And you can see there's my dy d theta right here, and here's my dx d theta there, and so I'm just dividing those two here. And isn't this kind of neat how that cancels, and the 1 plus e cos theta squared cancels, and so we end up with cos theta plus the eccentricity e over negative sine theta, which we can leave it that way, and we have another way of writing it. We could write it as negative cotangent theta minus e cosecant theta. So both of these are useful ways of looking at it, and that answers that first question. The dy dx actually is given here in terms of theta, so we'll actually need to look at what the true anomaly or that angle theta in standard position is. We'll need to know that angle theta there. And as that theta changes, that angle theta changes, we'll be able to find the slope dy dx. Let's take a moment here to quite literally go off on a tangent. So this is the slope of the ellipse, and if the ellipse has eccentricity 0, that's a circle. So if E here was 0, this last term cancels out, and we're left with the slope of the tangent as just negative cotangent. That is the slope of the tangent of theta, 0.63. And this line, this is the tangent of the circle, its slope is the negative of cotangent of theta, here negative 1.58. And when you multiply these two slopes together, you'll always get negative 1 because these are perpendicular lines. Tangent and negative cotangent, when multiplied together, of course, always produce negative 1. Now I'll go back to number 2. An elliptical transfer orbit from Kerbin to the Mun has a semi-major axis of A equals 68 kilometers, eccentricity of E equal 0.885. Compute the slope of the tangent to this orbital path at true anomaly 90 degrees. So we just figured out what dy dx is, and well, so if the angle is 90 degrees, then it's the cosine of 90 degrees plus the eccentricity, which we know in this case 0.885 over negative sine of 90 degrees. Well, let's see, cosine of 90, that's equal to 0, so that crosses out. This is sine of 90, that's equal to 1, so we got negative 1. So this simplifies to negative 0.885. That would be the slope at a true anomaly of 90. Let's make sure that you got the idea what we're talking about. So in the elliptical orbit, we've actually got the planet at the intersection of the x and y axes, and we've got some other focus out here. The ellipse is something like this, and at the point that the true anomaly is 90, right there, at that point, the slope of the tangent right there, slope, is negative 0.885. I'm going to see that show up later back in the game, so we'll come back to that. Let's move to number 3. Find the true anomaly at the instant the slope of the tangent in the xy plane is 0. So find the true anomaly when the tangent slope is 0. So basically, if you've got this elliptical orbit, so what we're looking for is this angle theta here. This is the true anomaly at the instant when the slope of the tangent in the xy plane is 0. So we're trying to find what angle when the slope is 0. So we've got dy dx given by this cos theta plus eccentricity over negative sine theta. And we'll set that equal to 0 to figure out what angle makes that fraction equal to 0. And that fraction is 0 when the top is 0 and the bottom isn't. So we can set that numerator equal to 0 and see what angle we get. So that would be when the cosine of theta is minus the eccentricity, which means when theta is the cosine inverse of negative of the eccentricity. In this particular case, that's when theta is cosine inverse of negative 0.885, which, well, that's about 152.3 degrees at an angle of 152.3 degrees. That's the instant for this particular elliptical orbit. That's the instant when we've got this slope that's 0. Let's move to number 4. What is the slope of the tangent in the xy plane at periapsis and apoapsis of the orbit? So the periapsis is the point closest to the planet, and the apoapsis is the point furthest. And we want the slope of the tangent in the xy plane at each of these points. Well, these are vertical lines in the xy plane. At each point you have a vertical tangent, so the slope is undefined. Actually, you could see that in the equation as well. Slope of the tangent, if theta is 0 degrees, which would be the angle of true anomaly at periapsis, we get e plus cosine of 0 degrees, and on the bottom we have negative sine of 0 degrees, and that's right there where it's undefined because the bottom is 0. So this is e plus 1 over 0. And dy dx at 180 degrees, that's true anomaly at the apoapsis. Well, the sine at 180 is also 0. So both of these slopes are undefined. Let's look at number 5. In general, for any ellipse with eccentricity e, what's the slope of the tangent in the xy plane at a true anomaly of 90 degrees? So we've got slope of the tangent is always going to be this for any ellipse with any given eccentricity. We don't even need to know what the semi-major axis is. This will always be the slope of the tangent at any point theta determined by the angle from the primary focus. So if that true anomaly theta is 90, we plug 90 in here. We have e plus cosine 90 degrees, negative sine 90 degrees. So cosine of 90 is 0, the sine of 90 is 1, so we end up in every case that whatever the eccentricity of the orbit, at 90 degrees, the slope of the tangent in the xy plane is negative of that eccentricity. Now let's move on to look at the flight path angle. Phi is the flight path angle, and it's the angle between the velocity vector and the horizon. And you can visualize that here. So here's the planet, and this is an orbit, and here we have the horizon. So if you were standing on this point, you look straight out. That's the horizon. You look straight up. You'd be at this point B, and this is where the rocket is currently, and this is a vector that indicates the velocity. So this line is the horizon, and this line parallel to the horizon is the local horizon. And the angle between the velocity and the horizon, that's the flight path angle. That's the angle that I'm calling phi. That. So we could figure out that angle phi at any point along an elliptical orbit. And the way you can do that is with this relationship that the tangent of phi is always 1 over r times the derivative dr d theta. To justify that formula that the tangent of the flight path angle is 1 over r dr d theta, let's take a look at this diagram. So down here we can see the planet Kerbal, and we've got this vector r that points to the location of the rocket on this elliptical orbit. So here we have the velocity vector, it's the direction we're traveling. The slope of that line would be the dy dx that we've been working on. So as r changes, there'll be a change in the angle and there'll be a change in the value of r. So that increase in the r is this differential in r. And this base of this triangle is this length r d theta, which is the length of a sector of a circle which has radius r. So as d theta and dr become very small, this formula becomes exact. So here we have number 6 says r equals a times 1 minus e squared over 1 plus e cos theta. That's the polar form of an elliptical polar form of an ellipse, and in this case describes an elliptical orbit. Let's let's find this 1 over r dr d theta expression. So why don't we just do dr d theta first? This is taking a derivative with respect to theta, where a and e are constant with respect to theta. So, well, what we could do, maybe better, let's rewrite it. So we've got a 1 minus e squared, and then let's write it as 1 plus e cos theta to a minus 1 power. That way we don't have to do quotient rule, we can just do power and chain rule. So dr d theta, this is all constant here at the beginning. So we have a 1 minus e squared, it's constant. And now by the power rule, the negative 1 comes down in front. 1 plus e cos theta stays there. Subtract 1, we get minus 2. And then the chain rule is going to give us a derivative of the inside. The derivative of 1 is 0. The derivative of e cos theta is negative e sine theta. And now that we can simplify. We've got two negatives here that'll cancel. So let's write this as e sine theta on top and 1 plus e cos theta all squared on the bottom. And we're not quite done. We still have to get 1 over r times this. So we know that tan phi is 1 over r dr d theta. And we've just done dr d theta there, and r, of course, is given here. So because it's 1 over r, I think what I'll do is I'll just flip that, and that's the reciprocal. So flipping this expression that I have here for r upside down, it'll be 1 plus e cos theta on top, and a 1 minus e squared on the bottom. And now this expression that I just got for dr d theta, that's a times 1 minus e squared, e sine theta on top, and 1 plus e cos theta all squared on the bottom. And of course that's going to cancel with that. And these guys are the same, so this one factor will cancel with one of those with one of the two factors. And so we'll be left with e sine theta over 1 plus e cos theta. So my conclusion is that the tangent of phi is e sine theta over 1 plus e cos theta. And so this is the 1 over r dr d theta that this particular question was looking for. And the reason that's important is because that's equal to the tangent of the flight path angle. So when I go back to number 7 now, use the relationship that the tangent of phi is 1 over r dr d theta to find a formula for the flight path angle of an orbiting spaceship. So first we write what we just concluded, that the tangent of phi is e sine theta over 1 plus e cos theta, and now you can solve for phi. It would be the tangent inverse of e sine theta over 1 plus e cos theta. So now we could use this to find the flight path angle in any elliptical orbit with some eccentricity e. And it would be, we would need to know what the angle of true anomaly is to calculate that. So what if the orbit was circular? So then the eccentricity is 0, and so this simplifies pretty quick. We'll say tan inverse, if you have 0 eccentricity, so orbit circular means eccentricity is 0. So you're going to have 0 on top, 1 plus, that's 0 times whatever the cosine of the angle happens to be. So this is tan inverse of 0, and that's 0 degrees. So the flight path angle remains 0 the whole time. That makes sense because as we're going around in a circular orbit, this is the position vector and this is the velocity. You're exactly in the direction of the horizon. So the angle to the horizon is 0. Flight path angles remain 0 all the way around that circular orbit. So the horizon and the velocity, they're parallel, and the angle between them is 0. So now let's look at this one. A crew of Kerbal astronauts on a journey from Kerbin to the Moon in the Unity Mach 4 rocket follow an elliptical transfer orbit with semi-major axis 68 kilometers, eccentricity 0.885. That is the orbit that I was in the video that I'm showing with the game that I'm playing right now. So we'll compute the flight path angle for this trajectory at true anomaly 90 degrees. So flight path angle is tan inverse of E sine theta over 1 plus E cos theta. So in our example, that's tan inverse of eccentricity 0.885 times the sine of 90. The sine of 90 is 1 over 1 plus 0.885, and we've got the cosine of 90, yeah, and that's 0, so none of that really matters. So we're looking at tan inverse of 0.885, and that's 41.5 degrees. So that'll be something we could check in the game to make sure that that's actually what's happening. At true anomaly 90 degrees, flight path should be about 41.5 degrees. And let's do this one, number 10, while we're here. So flight path angle is also called the pitch. So you can see that in the nav ball in Kerbal Space Program. You can see what the pitch is. And it says, what's the maximum pitch for the rocket during that whole transfer orbit? And at what angle of true anomaly does this occur? Well, what we're going to do is we've got phi is tan inverse of E sine theta over 1 plus E cos theta. So if we're going to find the maximum value of phi, we'll need to take a derivative of this with respect to theta to see how phi is changing with respect to theta, to see what angle we have a maximum pitch, maximum value of that phi. So the derivative of phi with respect to theta is a derivative of the tan inverse. When you do derivative of tan inverse, you get 1 over 1 plus whatever is the argument of the function squared. So in this case, E sine theta over 1 plus E cos theta. It's all squared. But the chain rule is going to apply here. We'll have to do a derivative of what's inside the argument. The derivative of that, well, that's going to take quotient rule. So we'll take the denominator of what's inside and square it. So that's 1 plus E cos theta all squared, and I just copy it again as quotient rule of this fraction. Now I need to do the derivative of the top. That's E sine theta. The derivative of sine theta, that's cos theta. So we'll get E cos theta here, and then we'll do minus in the quotient rule. The top, the numerator, times the derivative of that denominator in the argument there. So that's the derivative of 1 plus E cos theta. The derivative of 1 is 0. The derivative of cosine is minus sine, so we're going to get a negative E sine theta there. Okay, so then I'll speed up the rest of this, just simplifying, distributing on top, and you notice that there's a cosine squared plus sine squared we can factor out up there on the top. So that's where I get that 1. And I'll just multiply out the bottom. And so we're trying to figure out when this derivative is 0, which would happen when the top is 0 and the bottom isn't. So let's set that factor there on top equal to 0. And this should start to look kind of familiar, right? We're going to look for when the cosine is minus E. So that is theta, when theta is the cosine inverse of minus the eccentricity, and that eccentricity is 0.885. So yeah, we've been here before. That's an angle of 152.3 degrees, which is exactly the same point where we had that slope of the tangent equal to 0. When the tangent was horizontal on the xy plane, that's exactly the same point where we have the maximum pitch. Let's go back to the Kerbal Math and Physics workbook and click on this link here, flight path angle. We get this graph, and you can experiment with what the flight path angle would be all the way from 0 to 360 degrees, one revolution around any planet or moon, and you can set the eccentricity to whatever you want. So let's put it to the eccentricity that I had on this particular flight, 0.885 roughly, and from there I can now actually confirm what is the maximum. It happens at an angle of 152.3 degrees, and actually the angle is about 62.3 degrees. The maximum pitch is 62.3. It occurs at a true anomaly of 152.3 roughly. I have that here in this graph. I can change the eccentricity, and I can change the semi-major axis, and I can move this point where the rocket is all along, and I can see now that when that angle of true anomaly is about 90 degrees, that flight path angle is about 41.5 as expected, and then as we're traveling along this path, that angle, that flight path angle increases. Here it is at 59, 60. It's going to go up to about 62. And that happens at about 152. See, I see the true anomaly down here, about 62.3, right when that's about, so that's about the maximum right there, and then it's going back down. Yep. So when the true anomaly is about 152, the maximum pitch occurs, which is about 62.3 degrees. Okay, I know this is just a monstrously long video, but there's this one more thing that's just really fascinating to me that I want to put in here. I've got included, as the rocket follows the elliptical path, I've got mean anomaly and eccentric anomaly also visualized here. I did a separate video on what these angles are and how they relate, but let's just do this one thing here where we can discover here that when we're at that point where we have the maximum pitch, and the slope of the tangent is 0, that point that I'm going to look for in the game, when that hits 90, I can't get it to be exactly, but let's say at 90, I expect the mean anomaly to be about 39.4 degrees, and at that point where we hit the maximum pitch, I know the eccentric anomaly is 90 degrees. And the reason why that could be significant is that we can then go back and calculate the time, how long it will take to reach that point. So we could see that also in the game. So I did that, and the way you could do that is that if you knew at that moment of maximum pitch, eccentric anomaly is 90 degrees or pi over 2 radians, I can calculate the mean anomaly. Actually, I could also see the mean anomaly in my graph. It's about 39.4 degrees. But I need it in radians here because what I want to do is compute the average angular speed based on the gravitational parameter and the semi-major axis. And with the average angular speed and the mean anomaly, dividing those, it tells me how long it takes until I reach that point in the orbit. So that's about an hour and 30 minutes. So we had passed the periapsis at 31 minutes of mission elapsed time. So if I add on another hour and 30 minutes, I can expect the max pitch to occur at 2 hours and 1 minute in the game. So now let's see if that really works out. So now, looking back, we can check mission elapsed time, the semi-major axis, the eccentricity, and current true anomaly. And the first calculation we can confirm here is pitch at true anomaly of 90 degrees. We had calculated an angle of 41.5 degrees pitch, assuming the rocket is pointed prograde, that is, in the direction of its velocity, when the true anomaly was 90 degrees. Next, we had calculated that the maximum pitch will occur at mission elapsed time of about 2 hours and 1 minute. So I'll fast forward the video here to reach that point. We had determined at a true anomaly of 152.3 degrees, the maximum pitch of the rocket would be 62.3 degrees. Technically, this is the maximum angle during the orbit between the velocity vector and the horizon, or perpendicular to the radial vector. Note this is occurring as predicted when the eccentric anomaly is 90 degrees and mean anomaly is about 39.4 degrees. At a mission elapsed time of about 2 hours and 1 minute. Also worth mentioning, you might have expected this maximum pitch to occur at halfway through the trip to the moon, since it is halfway along the elliptical path. But actually, as the distance from Kerbin is increasing, the rocket is slowing down. We can see the total orbital period for the orbit is 2 days, 1 hour, 52 minutes. However, this is measured in Kerbin days, which are actually only 6 hours long. So that's a complete round trip or orbital period of a little over 13 hours. A trip to the Mun is therefore half of that, or almost 7 hours. So after 2 hours, when it appears we are halfway there, because the rocket's speed will continue to decrease, it will take another 5 hours to reach the apoapsis, or furthest distance from Kerbin. But actually, before that happens, we will intersect the Mun's sphere of influence and be captured by the gravity of the Mun and need to slow ourselves down to get into another elliptical orbit about the Mun. Okay, so here we are now approaching the Mun, and as we approach, we perform a lunar orbit injection burn to slow down to a speed sufficient to be captured by the Mun's gravity. Kerbal Space Program, a perfect textbook model of Newtonian physics. In the next episode, we'll land on the Mun and do some navigation, exploring around the Mun, see what we can do there, what we can find on the Mun. So thanks very much for watching. I hope it's been interesting and you've learned some calculus and some rocket science. It's been fun to go through and learn this for myself and to present it. So I hope you enjoyed it.